Hi, fifth graders. It's me, Hadley, again, and this is lab number 2, where we are going to look at the law of conservation of matter. It's also known as the law of conservation of mass. And for this lab, you are going to need a few things in your kitchen. It's very simple kitchen science. These are very simple little experiments, but you should have some white sugar, granulated sugar. You need to have any kind of plastic clear cup is nice. You can use glasses at home if you want. Having them a little shallower is kind of nice. You're gonna need some water. I just have water right here. You're gonna need, I have, what is this? A quarter cup. I've got some balloons. You can do this or not. I'm just gonna do a little experiment with balloons and vinegar and baking soda. And I have a small mouthed bottle that we're gonna use. And I am gonna use this scale. I know not everybody has a scale at home. Some of you might have an even better scale. This isn't the best scale in the world, but we're gonna weigh our reaction before and after. So with that, let's get started. I am going to turn back to my iPad, doing some screen sharing with you, and I'd love for you to take notes in your science journal. So let's get started.
Looks amazing.
All right, fifth graders, you're probably wondering why I just showed you that clip of Bumblebee transforming into a robot. But it has everything to do with the law that is right in front of you, called the law of conservation of mass, which states that matter can neither be created nor destroyed. In a closed system, the mass of matter involved in the transformation or reaction cannot change, regardless of how it is rearranged. All right, so what I'd like you to do is take notes. I'd love for you to write this law down. But what you watched with Bumblebee is you noticed that when Bumblebee went from a Volkswagen Beetle to a robot, no part of that machine was created or destroyed. You did see that one part fall off in the very beginning, but it was incorporated back into Bumblebee when he became a robot. So I just wanted to share that with you because that perfectly explains the conservation of mass. Okay, so Bumblebee is the same weight as a car as he is as a robot. So the same thing can be true in chemical reactions. So I want you to imagine, this is going to be a little math problem, and I'd like for you to write this down. But let's say you're mixing chemical A with chemical B, and you get a reaction. This mixes, and there's some kind of crazy chemical reaction. And from that, you get chemical C and you get chemical D. But do you see this equal sign? This means that the weight of these chemicals equals the weight of these chemicals. Okay? So another way to write this is, and I want you to take notes doing this too, you're going to write mass of reactants, which are the chemicals that you are mixing together to cause a chemical reaction, equals the mass of the products, which is the resulting product. So here's another example, and we're actually going to do this with kitchen science today, but I just want you to take notes on this too. Let's say you have a cup. This is my cup. It's not a very good cup. And inside my cup, I have water. And I'm going to say I have 125 grams of water. Okay? And then I want to add sugar to this water. Here's my pile of sugar. Okay? This is sugar. And I have 25 grams of sugar. And so then here is my chemical reaction, and it is a chemical reaction because that sugar will completely dissolve in the water and it'll become sugar water. You won't see the grains of crystal or the crystals of sugar anymore. Sugar water. How much do you think this should weigh? If you guessed 150 grams, you are correct. All right, so now we're going to actually do this little experiment, and we will actually do another experiment to see if this law is actually true. Hi. We are going to work on this experiment now. And what I have here, I've got a tablespoon, and I have some glasses, I have water, and I have sugar, and I have this cool little scale. And it turns off and on a lot, so I might have to fiddle with it a little bit. But right now I'm turning it on, and I'm tearing it so that when it has this plate on it, the plate makes it's zero weight right now. So when I start adding weight is when I add the weight. There's a lot of things that I need to keep consistent here. So I want to make sure that when I have my experiment that everything is the same between the reactants and the products. I'm going to explain this a little bit in more detail. So what I'm first going to do is I'm going to put water in here, and I'm not really going to measure it until I put it on the scale. So this already went to off. Turns off really easy. Okay, I'm going to put this on here, and it says I have 155 grams of water. Okay. And now what I'm going to do is I'm going to measure 1 tablespoon of sugar. There's a cup in there. Let's see. This is a very flimsy cup. There we go. And I'm actually going to put this whole tablespoon on here because it has to be the same before and after. And it just went to 175 grams. So that is 20 grams of sugar. And now what I'm going to do is I'm going to mix. I'm going to put that in there. This is my chemical reaction time now. I'm going to keep the spoon there because it needs to be the same before and after. And I'm going to stir this up. And you can see my weight goes up and down because my spoon is hitting the scale. But it's going to take a little bit of time for all of that sugar to dissolve. And pretty soon you're going to see no sugar crystals in there anymore. We might do a fast forward. All right, now it's starting to clear up. You see that there's no sugar in there, so a chemical reaction just happened. We just created a sugar water solution. I see no crystals of sugar in there. And my scale, it says 170, which indicates that it did change. I think the scale isn't perfect, but it really should be 175 there. There was 175. If I had better scales, this scale only moves in 5-gram intervals. I really wish I had a scale that went in much smaller, like hundredths of a gram would be really, really great for science. But you can see that it just changed back to 175. So you can see that the matter was conserved. The mass was conserved from the beginning of the reaction to the end of the reaction. All right? All right. I'm going to do another cool, fun little experiment. It's everybody's favorite kitchen science experiment, really easy with products that you probably already have, baking soda and vinegar. And we all know what baking soda and vinegar does, but I want to see if we can kind of prove this law of conservation of mass with this experiment. It's going to be a little bit hard with this scale. If you guys have a scale that goes to 100th of a gram, that's much better. This scale might not be able to detect the escaping of carbon dioxide, which is what's going to happen here. Okay, so we want to prove that the mass of the product of the reactants equals the mass of the products, or in this case, because we're going to let the carbon dioxide escape, it might not equal, because we're going to have the carbon dioxide escape the system of this bottle into the system of the air. So I'm hoping that at the end, the mass will go down. I hope I'm explaining that fine or okay for you. So I'm going to turn this on. Well, actually I'm not. I'm going to use a funnel, and I have a 1/4 cup of baking soda that I'm going to put in this cup, in this bottle, I mean. And it takes a little practice. You can see I already spilled when I was practicing this a little bit. So you just have to let the funnel, if you don't have a funnel at home, which I don't think I have at home, you can just use a piece of paper and make your own funnel out of a piece of paper. It's finally going through. Okay, so we did that. And I'm going to put that on the scale. Whoops, I'm going to tear the scale first, okay, and make it go to 0. And it says I have 95 grams of baking soda and bottle, okay. I'm not being very clean as a scientist, I'm sorry, but it's just baking soda. Okay, so what I'm going to do now is I'm going to put a 1/4 cup of vinegar on here, and I'm actually just going to put this on the scale right here. Okay, putting it on the scale, and now it says it went from 95 to 160. So this right now is the mass of the reactants. Okay, and yes, it's including all the plastic, because you have to do that because you don't want those to be negating anything. Okay, so now what I'm going to do, and this is where I hope that this number goes down. It's going to go down when I lift things up, but when I put everything back, I'm hoping that number will go down. Okay, let's see what happens. I'm going to carefully, you can see the reaction happen. All of that carbon dioxide is escaping. And of course, on my scale, you cannot see the change of carbon dioxide. But if I had a more precise scale, that number would go down. But carbon dioxide doesn't weigh very much. It's a gas. It's now in the air. So if I change this a little bit, it did go down to 155, which, you know, maybe that's the carbon dioxide escaping, but that's one way that we can see, and I can smell kind of the vinegar, carbon dioxide in the air. So in this case, it looks like the mass changed, but it really didn't. Now I want to keep it in a closed system. And this is how scientists actually discovered a lot of things about chemistry, because they created closed systems. And so how I'm going to create a closed system is by using a balloon. I'm going to stop this, clean up, and then we're going to do another little experiment. Okay, I am back, and now we're going to create a closed system, okay? And so here's what I'm going to do. I'm going to put, this time I'm going to put a 1/4 cup of vinegar in the bottle. You know, I'll keep it consistent. I'll make sure this works. Okay, so, and I'm going to put the bottle on there and measure. And it says that I have 70 grams of vinegar and bottle, okay? And now what I'm going to do is I'm going to take my balloon, okay? And this is going to make my closed system. Now the carbon dioxide won't be able to escape. I want to see how much it weighs with the balloon on there. I have a feeling it's not going to measure the balloon. If I had a better scale, this balloon would be measured. But anyway, so it doesn't change with the balloon on there. Okay, and what I'm going to do is I'm going to take a 1/4 cup of baking soda. And this is where the funnel is really handy. Okay, whoops, I'm kind of a messy scientist. I'm going to put the funnel into the balloon, and then I'm going to put the baking soda here. And it's actually kind of a lot of baking soda for the size of this balloon, but hopefully it'll work. Because of this, I've decided I'm going to put a little more vinegar in here, so the reaction can be bigger. It doesn't really matter as long as we keep looking at the weight. So 110. Okay. It's still going in there. Still working its way. All right, I'm gonna do a little less. The amount of baking soda and vinegar doesn't really matter. But what I want to do is now I want to put this on here and weigh it. So it went from 110 to 135. So I'm hoping that after this experiment, we're going to stay at 135, because this is going to be a closed system with this balloon. All right. So the number is going to change a little bit while I fiddle with this. But now what I'm going to do is I'm going to stretch this balloon over the top here. I hope I have enough vinegar in there. Okay. And now I'm going to shake the vinegar into the thing, and look what happens. Woohoo! And look, my numbers didn't change. We're at 135. We have a closed system. We did not let the carbon dioxide escape into the room. Oh, it went down a little bit, but maybe it'll go back up to 135. It went back up to my dumb scale. I'm sorry, but I think you get the idea. Here is a closed system. We put vinegar and baking soda into this system, and now it's a totally new product. I forget what the mixture is called when you mix baking soda and vinegar. I'm going to look that up and I'm going to tell you in a minute. I just can't remember what it is at the moment. We have the carbon dioxide in the balloon, and it is a closed system. So it keeps going down a little bit. It's just because the scale isn't very good. But anyway, that's kind of how the law of conservation of mass works. All right. This is a little bit more complicated, but I want to just show you so you can understand, based on when we were working with compounds. Here's a compound and here's a compound right here. I'm just going to show you how this reaction works. Okay, So with baking soda is right here. This is baking soda, right? Okay. I'm just going to change my pencil to here so I can show you where I am. I've got baking soda, which is sodium bicarbonate. And this is the chemical symbol of sodium bicarbonate. We've got sodium, hydrogen, carbon, and oxygen with sodium bicarbonate. Okay. And notice that we have one sodium, one hydrogen, one carbon, and 3 oxygen right there. And then we're adding vinegar. You can see that we're adding vinegar, which is acetic acid, which says that it's HC2H3O2. So we have 1 hydrogen, 2 carbons, 3 hydrogens here, and 2 oxygens. And the most important thing is here's my chemical reaction. This equal symbol. Check this out, okay? Now, it changes. Here are the products. The products are sodium acetate, water, and carbon dioxide, okay? I want you to notice. So in this system, if it was a closed system, if it had balloon capturing that carbon dioxide, the mass here equals the mass here, okay? But I want to show you something really cool. How many oxygens are up here? We've got 1, 2, 3, 4, 5. How many oxygens do I have down here? 1, 2, 3, 4, 5. It's the same. Look at the sodiums. Here's my sodium. How many sodiums do I have? I have 1 sodium and I have 1 sodium. You can hear the bells here at the Jackson Hole Children's Museum. Okay. How many hydrogens do I have? I have 1, 2, 3, 4, 5. Let's see. 1, 2, 3, 4, 5. See how that's all equal? And then carbons. There's 1 carbon, 2, 3, 1, 2, 3 carbons. So you can see that the mass is conserved and even the atoms are preserved, but the product changes. We go from sodium bicarbonate and acetic acid to sodium acetate, water, and carbon dioxide. Isn't that so cool? Okay, so just to clarify, here's our baking soda and vinegar. I'm going to just change this to black so you can see. Here's my weird bottle. Okay, this is a bottle, believe it or not. And this is an open system, so I put my baking soda and then I fill it with vinegar, and we have this reaction that happens and the carbon dioxide escapes, okay? So this is an open system, and the mass of this system will be less because the carbon dioxide escapes. But if I have my closed system right here, here's my bottle, and here's my balloon. Okay, here's my baking soda, here's my vinegar, here's my chemical reaction, and here is all the carbon dioxide. This equals a closed system where the mass equals of the reactants equals the mass of the products. Does that make sense? Okay, that's it for lab number 2. I hope you had fun. Bye.